Hi everyone, thank you for joining me today. My name is Mateusz Szafoni. In this presentation we will explore the current progress of x86-64 port in Apache NuttX. For convenience in this presentation I will use the term x64 to refer to x86-64 architecture. At the beginning, a few words about me. I am NuttX contributor since 2016. I work with NuttX for fun, and that's where most of my contributions to this project come from. But also I work as an independent contractor trying to use NuttX wherever possible. The presented work is the result of my collaboration with Xiaomi. So from my side, thanks to the Xiaomi team for the code review, suggestions and testing. Some of the changes mentioned during this presentation are already in the NuttX upstream repository. The rest will be added in the coming weeks. So let's start with ACPI support in NuttX. ACPI is a component present in almost all modern computers. It is standardized interface used to perform power management, device discovery and configuration tasks. For now we are only interested in hardware components discovery feature. This means that what we need is to extract some data from memory that are provided by BIOS in a format of ACPI tables. That's why a simple custom ACPI parser was implemented. Alternative for this custom solution was ACPI CI project, which is an open source OS independent ACPI implementation. So why didn't I choose this solution? There are two reasons. First, we only need a small piece of its functionality which can be easily implemented. Second, it doesn't follow the NuttX coding standard. To parse ACPI tables, first we have to locate special RSDP signature in the memory. Currently, it's supported to search for this signature in a legacy BIOS area or get it directly from the multibot tag. At the moment, ACPI parser is located in the x86-64 architecture directory, but in the future we probably should move it to a location available for other architectures. Here we can see an example dump of ACPI tables for QEMU. If necessary, the tool can be improved to display more details from ACPI tables, but for now the current functionality is sufficient. HPET is 64-bit up counter timer. It's a hardware timer located on the chipset, so access to it is over memory area, unlike the TSC timer, which is an on-die timer on modern x64 processors, which can be accessed by CPU registers. In NuttX, HPET is implemented as one-shot timer and work in one-shot mode with legacy interrupt support enabled. HPET comparator triggers interrupt on equal condition, not greater or equal, which is a huge design flaw which can lead to interrupt miss in one-shot mode. To prevent this, we must explicitly specify the minimum supported interval for a given platform in the configuration so that the comparator update always triggers the interrupt. For example, for QEMU, this value is quite huge, around 1000 microseconds, but run directly on the Intel processor that I have around is around 10 microseconds. It's worth mentioning that HPET in some processors is unstable, and in Linux kernel it's blacklisted for some Intel CPUs. Now a few words about math acceleration in x64 processors. I will deal with two types of hardware acceleration in x64 here. The first is legacy x87 instruction set, which is not as essential after making SSE2 available by default in x64 according to specification, but still can be useful for some high precision calculations. And the second one are SIMD vector instructions. SIMD instructions are disabled by default until the operating system explicitly enables them. Support for SSE instructions above SSE2 was trivial, and it came down to adding some compiler flags. AVX support required more work, and a new method of saving FPU context had to be supported, which will be discussed in the next slide. Support for a given instruction set must be enabled from the NuttX configuration level, and NuttX configuration must match the features supported by the processor. There is no dynamic selection of supported CPU features. So if we enable a specific instruction set in the configuration but it's not supported by the hardware, NuttX crash at the early boot step. Unfortunately, at this boot stage, serial port is not available, so we don't get any valuable error message. CPU state must be saved during context switching. That means also vector registers must be saved and restored. AVX instructions require new xsave and xrestore instructions, support for saving and restoring CPU state. Xsave has different requirements than the previously supported by NuttX fxsave instructions. It needs 64-byte alignment buffer, but fxsave needs 16-byte alignment. Xsave buffer size depends on the system configuration and set of enabled features, while the buffer for fxsave has a fixed size. Some additional control registers must be configured for xsave, and each xsave call behavior is controlled by EDX and EAX registers that must be written on each xsave call. For now, only standard xsave instructions are supported, so there is no support for optimized version of these instructions. When it comes to math library support for x64, we have two reasonable options to choose from. The first one is OpenLibM, which uses x87 legacy instructions for many math functions. And the second one is newlib library, which depends on compiler optimization, and compilers prefer to use vector instructions. NuttX math library is also supported, but it has limited functionality and is not x64 optimized, so its use in real-world application is limited. I also experimented with the host toolchain libm. Unfortunately, it doesn't work. The host x64 math library is tightly coupled to the host libc, which results in a lot of compiler errors. Optimized string functions were ported from Bionic project, which is an implementation of the standard C library developed for Android, which is BSD license. Optimized functions used vector instructions and can be enabled when a given x64 vector extension is enabled in the configuration. Unfortunately, the FPU test from NuttX OS test doesn't work for x64 when high optimization level enabled. The problematic part of the code is present on the left screenshot. In short, how this part of code works. First, we perform some floating point operations and locally store FPU context. Then force the program to do some context switches. And finally, compare the current FPU context with the previously saved one. If everything went okay, the FPU context should be the same and the test succeeds. The reason of this failure is the for loop presented on the right screenshot, which is executed when sleep is called. The compiler uses a loop vectorization technique for optimization, which uses vector instructions, the same vector instructions used for floating point calculations. This results in modified FPU context, which breaks FPU tests. On this slide, we can see core-mark result for Linux and NuttX. We can see that Linux performs better and is better about 6%, so there is still room for optimization somewhere, but I haven't explored the reason for this difference yet. And changing optimization flag to 03 doesn't make too much improvement for the NuttX result. Now let's talk about SMP. In x86 terminology, the bootstrap processor or BSP is the first processor that is booted. All other processors are called application processor or AP. This BSP in SMP initializes each core's private data and wakes up the AP cores with inter-processor interrupt. To send API to the processor, we need to know its local APIC identifier. This is where we need the previously mentioned ACPI. The BSP reads the local APIC ID value for a given core from the ACPI table and creates a map connecting the local APCI ID with the logical CPU ID. To optimize SMP performance, we use the special purpose GS register to access frequently used data such as current rex and CPU ID. This is a popular OS dev technique for x64. In x64, FS and GS registers are used for a limited form of segmentation. We use special instruction to save the base address for FS and GS, and we can later refer to the data stored at this address in a simplified way. The images show access to current rex stored in private CPU data and the generated assembler codes that use the GS segment. The FS register is not yet used and is reserved for 3 local storage implementation. Here we can see result of PS command run directly on Intel i7 processor with 12 cores enabled. The system passes the SMP test present in NuttX apps correctly, but the output of this program is too long to fit on the screen. Here we can see CoreMark result with 12 cores enabled. Linux also performed better in this test, scoring about 10% better than NuttX. Now let's move on the important element of every x64 machine, which is PCI. Probably every x64 application requires some degree of support for PCI devices. Support for MSI and MSI-X has been implemented, as it is currently the primary interrupt method for PCI cards. Legacy PCI interrupts are often not even supported by new hardware. But this old interruption method is still used, for example, by some of the QEMU drivers. MSI support required some improvement to x64 interrupt logic, such as support for all possible interrupt vectors and dynamic vector allocation. To communicate with real hardware without a legacy UART port, it was necessary to implement support for PCI serial card. Currently, cards based on AX99100 and QEMU simulated PCI serial device are supported. In addition, support for Intel i219 and Intel i225 network cards was added. Their implementation is based on NuttX NetDev upper half logic. For now, no advanced card features are supported. Side note from me, Intel network cards are terrible mess. Some have undocumented hardware bugs, some cards from the same family but a different series may not work with the same driver. Sometimes it's really hard to find the reason for the problem, and often you won't find the solution in the Intel documentations. Kernel mode is still under development. Initial RAM disk is supported with multi-boot header, so we can easily include RAM disk with group. ELF support was ported from x64 simulator, and per task address environment seems to be working properly. What is missing is syscalls and support for ring 3 privilege mode. Now, important note about security. Currently there is no protection against speculative execution vulnerabilities such as Spectre or Meltdown. While some issues have been fixed in newer Intel processors, Many of these vulnerabilities still require fixes at the operating system level. Implementing these OS level fixes often comes at the expense of performance, which is particularly problematic for critical real-time applications. This may or may not be a problem, it all depends on the application, so risk analysis must be done for a given use. A few words about what can be done in the future. First, we can add support for more PCI devices, including NVMe, CAN bus cards, USB and more. We can add support for graphical interface and keyboard support, so we can run NuttX directly on the hardware without need of legacy serial port or PCI serial card. Another thing is support for AMD processors, and of course we need more testing, performance optimization, more code review, and code quality improvements. Now some ideas for when we might need x64 with NuttX. When our application needs high computing power or requires a large amount of resources like RAM, flash, or a large number of cores. When we need to run simultaneously real-time operating system and general purpose operating system. In that case, we can use one of the available real-time hypervisors. In that scenario, we can separate critical real-time functionality from non-critical work. This approach can help us with safety certification when required for a specific parts of our product. Another case is when our real-time application needs to communicate with PCI Express devices like high-performance network interfaces, digital acquisition cards, or any other devices that can be implemented as PCI card. Maybe NuttX will become a good alternative to RT Linux in the future. Some more specific application examples are kind of industrial equipment like multi-axis motion controllers for robots or CNC machines, when in real time we have to control motors to achieve complex movements. Real-time Ethernet controllers, for example based on EtherCAT protocol. Advanced flight controllers for avionics or drones, so we can combine Linux tools like computer vision with real-time tasks like sensor integration, flight control, or others. Some laboratory equipment like data acquisition systems where we can use Linux as user interface and real-time OS for precise timing and data collection. Or even more exotic applications like high-frequency trading where low latency is crucial to make money. That's all from me. Thank you for your attention. If you are interested in the topic, I encourage you to test and help improve the x64 port in NuttX, as it may bring many interesting applications in the future. Thanks.